like this, then you can ask how the E prime transforms, right? Well, E prime will transform how? Well, I know precisely how the E transforms, right? E was transforming in the matrix notation again. E goes to RE, right? So this will go to SRE, right? But on the other hand, from this rule, I mean, now I want to rewrite that back in terms of E prime, right? Because now my new base is E prime, not E. But this is the same as SR, S inverse E prime, right? So that's what. So in the E prime basis, the corresponding, so I go to the E prime basis, then the question is how does the E prime transform? E prime goes to this matrix times E prime, right? So the R, original R, is transformed to SR S inverse. I mean, the new basis is that. So changing the basis is just the same as similarity transformations. Okay. So that's why we say that any two representations which are related to each other by similarity transformation, they are the same representation. They are not different representation, because effectively we are just choosing a different basis. No? So that's why I had that.
And that's the Schur's lemma. That's Schur's lemma.
That's Schur's
lemma. Yeah.
Schur's lemma, okay.
It's different.
Schur's lemma, I thought was more to do with the dot products, vector products, and so on, right? Schur's lemma. But
it depends.
I think there are many different Schur's lemmas,
yeah,
probably.
I've read.
Yeah, yeah.
And one of them, it's a
one of them is
like
that.
this. Wait a minute, maybe it's only this book. Okay.
All right. So now, that was, and then we showed that the complex conjugate representation of SU2 was in fact the same as the original representation, up to a similarity transformation. All right. Now let's discuss this the next chapter. One more thing, I should have mentioned that. This complex conjugate representations, okay, in the SU2 case we said it's the same, but this will not be true in general. In SU3, for example, they will be different. For some representations will be different, some representations will be the same. Like a joint representation will be the same. Complex conjugate representation of a joint representation is the same as a joint representation. But there are other representations which are not the same. Okay? Now, so this complex conjugate representation is quite useful in constructing invariants of the group. Okay? So the idea is the following. So remember, the complex conjugate representation was if I take R of some x is a Lie algebra element, x belonging to the Lie algebra element G. So R of x, then the complex conjugate representation was just replace this by minus Rx bar. Okay, that's how we did that. Okay, so but now, so what will happen? I mean, so if I have some vector space here, I mean, this is going to act on some vector space, right? So this will act like, I mean, as usual here already. When we this is some matrix, some n by n matrix. So you can always think of it as acting on an n-dimensional vector space, right? So it will be, if I write explicit, so it will act on some V, where V is n, so these are n by n. So this is an n-dimensional vector, column vector. And explicitly, what it will mean is that it will be some R, X, Ij, Vj, right? So the V will transform like that by this matrix. Similarly, here, again, there will be a transformation. And let me do the following. So again, it will act on some, I don't know, let's call it something else, W, let's say. Okay, some different vector space. Okay, the same dimensionality, but at the moment I don't know whether they are similarity transformations, right? In fact, sometimes it's not a similarity transformation. So just think of it as some different vector, W. And this is also going to act on that. It's again an n-dimensional vector, because this is also n by n. Okay. Now let's take a transpose of this. Okay. Let me symbol here. So let's take a transpose of this now. So what will I get? W transpose times minus R bar transpose, but R bar transpose is the same as R dagger, right? R dagger of X. And explicitly, let's write it down as W I. Let me just choose some different WJ, okay? And you have R dagger Ji. This is just a notation. I'm just using a notation where the representation itself was labeled by lower index, J. It doesn't matter, I mean you can put anywhere, but it's just convenient, that's all. And this one, I put it in the upper index, so by just looking at the index structure, you know it's a complex conjugate representation. Now let's take, so this is how transforms. V transforms to that, and W transforms like this. Now let's consider a combination which is Wi, Vi. By the way, this is the same thing is going to happen for the group. I mean, here I talked about the Lie algebra, but if you talk about the group, say G belongs to group, then this will be again Rg, Ij, Vj, and Wj. So this was X and Rj dagger I X G. Okay.
This here?
Sorry, no, this was minus. I should write it. So, what are we doing here? So, remember, to exponentiate the group, what we do, we write as e to the power of some I theta x, right? So, for example, think of x as sigma matrices. X is equal to sigma a's. So I will do this expansion. I mean, I will do that. But now, so when I go to when I take it in a particular representation R, it will be expanded as e to the I theta Rx, right? With a matrix R, and you expand that. And this is what we'll call, so let's say this is G, then we'll call this as Rg. Now, on the other hand, R bar, let's call it R bar G, which is the complex conjugate representation. Okay. There I will just exponentiate the complex conjugate representation of the X, right? So that will be e to the power of minus I theta R bar of X. No, sorry, e to the power of I theta R bar, which is the same as e to the power of minus I theta Rx. So what we are going to what we are seeing is that this object, if I compute this Wi, Vi, this combination, then this will transform like what? It will go like Wj, Rj, dagger I. That's the way W is transforming, and V is transforming as Ri. This one, where was the formula here? Here. Rik, Vk. Okay. And that is invariant. For example, for SU2, our dagger is the inverse, right? So this is exactly equal to Wj. So this becomes delta Jk. So this becomes delta Jk, Vk, which is the same as Wj. So what it's trying to show is that by taking a combination of the complex conjugate and the conjugate, original representation, you can construct an invariant. That is what I'm saying. Okay. I mean, this is useful, of course, for physics because, if you have you want to write on an action which is invariant under the symmetry, right? That's the whole point. Otherwise, you don't even call it a symmetry if it's not a symmetry of the action, right? Now, suppose you have some object which is transforming in some representation of the group. So, so what we are saying is that I can construct in the action. So suppose I start with some representation R, some field which is transforming in this representation. Okay. Then I can construct a phi, say the complex conjugate phi, where I'm just taking the trace like this, and that is invariant. So I can write down an action which consists of things like this. The D4x, or whatever dimensionality they are looking at. I can construct an object like this, which will be invariant within the symmetry. Yeah.
First of all, I couldn't keep track of the minus sign. When you said omega v is invariant.
So, sorry.
So, there must be a minus sign there or not?
Yeah, I mean this minus r bar. Remember, the r bar representation. R bar was by definition. Sorry. I mean here, what we are doing is that we are replacing this by the complex conjugate representation, which is this minus theta r bar. Sorry, right? That's right. Minus I theta r bar.
And in the same time, minus r bar g or r bar g.
R bar g. I mean, g is by definition e to the power of I theta x, right? So now what I'm doing is I'm just replacing x by the corresponding matrix in that representation. So in one representation, I'm writing it as Rx, okay? In the other, but this Rx is the same as is replaced by minus I R bar x in the complex conjugate representation. That is the meaning of this statement, right? So given a matrix, I get a complex conjugate representation by just replacing this by minus R bar x.
I mean, taking complex conjugate on the left hand side, R bar G makes both.
No, I'm not taking complex conjugate. I mean, there's no complex conjugate here. I'm just saying that in any representation, if I have R1 representation, it will be R1x. I theta R1x. If it's another representation, it will be R2x.
By definition of?
Yeah, by R2 I mean that minus R bar x. You see what I'm saying?
But I'm asking why don't we have a minus sign on the left side too?
Where?
R bar G, left side.
Yeah.
No, I mean this is okay. Let's not call it R. I mean bar kind of. I'm not taking any complex conjugation. I have an R1 representation and R2 representation, right? So here it will be R1 and here it will be R2, right? But now all I'm saying is that R1 I just choose my original representation R, and R2 it's complex conjugate representation. So complex conjugate representation by definition is defined like that, right? So in particular, what this would mean, so let's say for SU2, right? Let's take even the fundamental representation of SU2. So then this will be e to the power of I theta, say sigma 3, for example, or sigma, any sigma, or any combination of sigma, right? So this is now I'm taking an example of a fundamental representation of SU2. This could be done for any representation, but let's just stick to fundamental because then we can see more clearly. And now XA sigma A. XA are real numbers, right? Because otherwise you wouldn't get SU2 group. XA are real numbers. Now I go to the complex conjugate representation where this sigma A is simply replaced by minus sigma bar A. E to the power of, so this minus I just put it here, minus I. So this goes to theta XA sigma bar. And now, so this is how it is acting on W, right? But now what I do, I take the transpose. So this guy is acting on some W. So this is acting on W. Now I take the transpose of this, because this object which I wrote down, WV, is nothing else but W transpose V, right? So V is transforming like that. W transpose will be transposing like the transpose of that.
Vectors are all real, right?
Vectors need not be real. No, there's no.
You just take transpose. Not
Just take the transpose. Just take the transpose. Yeah, yeah. Exactly. So yeah, maybe so let's proceed with this. So we are saying that rule tells me that W goes to, V goes to e to the power of I theta xa sigma A, V. And W goes to e to the power of minus I theta xa sigma bar A, W. So now I take the dot product. This is why a dot product, I'm just calling it dot product, W transpose V, this combination, which is explicitly WIVI. That will go as what? I just take the transpose of this. So I will get here W transpose, and then transpose of this. Transpose nothing doesn't do anything to that, but this will make sigma a dagger, but sigma is Hermitian. Okay? So this simply becomes e to the minus I theta xa sigma A. And that V transforms like that, so you get here e to the I theta xa sigma AB. And you see that this cancels. So this way, we see that whenever you get a complex conjugate representation, there's a representation and a complex conjugate representation, you can take the inner product, the inner product between the two, which is simply defined as a transpose of the complex conjugate representation times the original representation. Okay? And this will be invariant. That is what we are saying.
So we have a condition here that the generators are real. Because
generators are Hermitian, yeah? Here.
Hermitian.
Sigma 2, I mean sigma are not real. Yeah, it was sigma bar A. The first thing was sigma bar A. So maybe I should have done it in 2 steps, right? So this was, I want to, the W is transformed like this. Now I take the transpose of this. Huh? So it will be e to the minus, e to the minus I theta xa sigma bar A, whole thing transpose, right? But then when you put the transpose inside, these are just numbers, nothing happens to them, right? I mean, this you can see, I mean, the exponential, remember, was just the, what do you call it, you can expand it, right, to any powers, right? But any power will be theta xa dot sigma bar A, whole thing to the power of n, right, or k or something, and sum over k. But each of those terms you can take the transpose, and when you take the transpose, you will find that all the sigma bar A's will be replaced by sigma dagger. Okay? No? I mean, take any generic term in this this object. A generic term of expansion will be minus I theta to the power theta xa sigma A bar A to the power of n over factorial n when I expand exponentially. Now I take the transpose of this. When I take the transpose, okay, of course this ordering will change, but all of them are the same, so it doesn't matter. So this will just become minus I theta xa sigma dagger A over to the power of n factorial n, which is the same as taking this dagger. But sigma dagger is sigma, so you get that. Okay. So for example, we'll see that when you talk about SU3, the quarks will transform as a triplet, 3-dimensional representation, which is the fundamental representation of SU3. Okay. But the complex conjugate, anti-quarks transform like from complex conjugate representation. That's what happens. But so you can take the inner product of anti-quark and quark and construct invariants. That's the
But when we're talking about them, they are complex vectors, I guess.
Yeah.
So they have complex entries, and when we are inner producting, we do the dagger thing, not the transpose one. V transpose times V.
No, that's the point of the complex conjugate representation. But effectively, complex conjugate representation already, when you say complex conjugate representation, effectively, you have taken already the complex conjugate. But they don't need to be the same field, you see. I mean, I could have, I don't know, some species of particle which is transforming in a triplet representation, and another species of particles, okay, which is transforming in the complex conjugate of that. It will be different species altogether. But I can still construct a taking the this product, inner product, this particular inner product, transpose, right? And then we see explicitly is invariant. Yeah, of course you could do that also. If you have a complex vector space, you can just take the dagger of that.
But using the dagger may ruin this proof.
No. I mean, that would be equivalent, you see. I mean, when I take the dagger, after all, this was a dagger of this object, right? Finally, that's what it is, right? So it's equivalent, actually, right? I don't think there's any difference.
No, because when we are taking transpose, we combine transpose with the sigma dagger and sigma conjugate, and we say that it will be a dagger and minus
that's right.
and plus negative.
That's right.
Yeah, but in that case, we will left with one more conjugation.
No. So no. I mean, no. You don't do this. I mean, when you take the dagger, it's already a row vector. I mean, here V was a column vector.
Yes, but the counterpart when it's transformed, it's like omega dagger times e to the something dagger. Can we also leave the same proof with the dagger? That's what I'm asking.
No, I mean, I don't know what to say. I mean, here I'm not thinking in terms of just everything is a column vector. No row vector. It's just a column vector.
It's the first set, but after transformations, after we do exponential times, we are looking if it's also invariant, and we construct that. We take transpose, we transpose e to the minus something transpose, but if you use dagger for inner product, then it will omega.
No, what I'm trying to say is that you don't take a dagger of W, because when you say W is transforming in the complex conjugate representation, it is already a complex conjugate. I mean, you see, if I take V, W is like V bar. So after that, you don't do another complex conjugation.
By conjugating the matrices, we also like.
Yeah, it's effectively that. It's effectively that. Yeah. So yeah, indeed, it will be complex.
Are W and V in the same vector space?
Sorry?
Are W and V in the same vector space?
They are all isomorphic, n-dimensional space, right? But the issue is how is it transforming? That's the point.
So I mean, are we dealing with only one vector space?
I mean, anytime you say it's n-dimensional vector space, then they're all isomorphic. They're nothing. What we're talking about here is how it transforms under the group, under the symmetry group. So yeah, here, I mean, when you say complex conjugate representation, it's effectively like, it's as if you are taking the complex conjugate of the original states. That's why it is transforming with the complex, complex conjugate transformation. So you don't do twice the same thing. I mean, you don't take a dagger of that. Once you say W is transforming in the complex conjugate representation, then you just take the transpose of it to get the inner product. Okay, now let me just go to I think today I should just finish that so that tomorrow I can start, next week I can start with SU3. So, just some basic idea. So here, so far we just talked about, let's say, I don't know, think about, like, say some particle is transforming in some representation of the group. And let's take fundamental representation of the Lie algebra. But then you might imagine a situation where I have a composite, right? Two of the particles get together, and you want to ask what is the total, how the full thing, the combined thing, right, transforms in the Lie algebra, right? So let's say I take some object which is transforming in the fundamental representation of some, like what we did before. Fundamental representation of some Lie algebra G, So how will it transform? It will transform with some in some representation. Not in fact, let me just call the full G, full group G. Okay. Then we can go to the Lie algebra also. But first, let's discuss the full group G. How will it transform? It will transform in whatever the representation is, in the fundamental representation. I'm thinking of fundamental representation. Although it doesn't have to be. You could choose any representation, it doesn't matter. But let's just start with the fundamental representation. RF of G, so some element G, right? Ij and Vj. It transforms like this. Okay. Now, if there is another object also which is transforming like this, okay, it will also have the same behavior. I mean, some W, J, Wi will also transform in the same way. Just replace this by Wj. This is also in the same representation. So imagine there are like two different particles or whatever. Something is transforming like this and transforming like that. But now I can talk about composites, but the composites is like taking tensors. Take tensors. So you can construct any arbitrary rank tensor, let's say I1, I2, I3, up to In. Okay. So this is the nth rank tensor by definition. How does that transform? This will transform by okay, this writing RF is very painful. So I1, J1, R, GF, RFG, I2, J2, and so on, RF, G, IN, JN, of T, J1, J2, up to J. So you see each of this index is transforming in the same way. So here you see what is happening here. The index I has transformed into index J with these matrices, right? But now I have many indices, not just one index, many indices, and all of these indices are transforming in the same way. Okay? Because the reason is because I'm taking the same representation for all these index. Everything is fundamental representation. So the matrix involved is the same matrix.
Okay. Is this guy a set of vectors that you can set of columns? I mean, and you can commute them and multiply them then with the matrices or?
No, this is just, I don't know. I mean, take for example, you must have seen tensors in various courses, right? For example, stress tensor. Have you seen stress tensor? No. Huh? Give me. The field strength you have seen, or the gauge field, F mu nu, right?
Yeah.
That's a second rank tensor. Okay, it is a particular tensor. It's antisymmetric. Here I'm not talking about asymmetry. It's it's just completely generic.
So it's like a matrix with the columns. Each vector we can put it in a column, and the rows are no, the columns are the number of n. Not n.
Mu say going in the four-dimensional, say electromagnetic field strength, right? Mu goes from 1, 2, 3, 4, or 0, 1, 2, 3. So 4 values, right? And okay, it was antisymmetric, no? But I mean, you don't need to, at the moment, you don't need to arrange it in a way. You are thinking of arranging like, you write like, I don't know, F0, 0, okay, 0, 0 is 0, so that I don't need to write because it's antisymmetric. You are thinking of writing like this, F01, F02, F03. Huh? Is that the way you?
Yeah,
right, F10, F10 is minus of that. You can write that, but I mean, you can, actually we'll see that, we'll try to write it in a way, I mean, yeah, you can do it any way you like. Huh? But the point is that there are these objects. How many such quantities are there? You see, if each of these i's, unfortunately I use n here. Suppose each of these I goes from 1 up to, let's say, d. D is the dimension of the fundamental representation, suppose. Then how many such objects are there? It will be d to the power of n, right? Because this guy can go from 1 to d, that guy can go from 1 to d. Each one of them independently can go from 1 to d. So the total number of components here will be d to the n. Right? So for example, if we just take n equal to 2, this guy can go from 1 to d. That guy can go from 1 to d, right? So how many possibilities you can have? D squared, right? if you don't have any symmetry properties. On the other hand, if you have a symmetric tensor, it will not be d squared, it will be half d times d plus 1, right? If it is antisymmetric, it will be half d times d minus 1. But at the moment, I'm not imposing any symmetry conditions. I'm not saying this guy is symmetric in the exchange of anything. This is completely arbitrary. Okay. So, for example, if I just take, I mean, maybe before going to n, let me just do 2.
But if we imagine that we have 2 columns, 2 vectors, and we just want to present them in a tensor, so we have only n d multiplied with n.
No, no. Because you can see, I mean, let's say, I don't know, let's say n is, d is 3, okay? So what can I have? 1, 2, 3, right? For this index. But then for each of this choice, I2 can be 1, 2, 3, 1, 2, 3, 1, 2, 3, right? Because they're independent completely. So for each of this choice of I1, there are 3 possibilities here, right? So 3 times 3. That's So as I said, I'm not imposing any condition. I mean, if you, for example, say that it is symmetric tensor, that means T12 equal to T21. Then of course I shouldn't count this guy and this guy as different, right? But I'm not imposing any condition. T12 may not be equal to T21. Huh? So completely generic tensor, second rank tensor, will have dimension d squared. That dimension meaning independent components will be d squared. So if you want to write it as a column vector, it will be a d square column vector.
But I guess compared to the previous transformation that we were doing, it's like that you got new interns where you're not supposed to put them.
No, you can go ahead, whatever you wish. I mean, this will just give me how, this will tell me for any g, how these tensors will transform, right? So, I mean, this whatever it is, it's again a linear combination of, let's take just 2 of them. Let's just take 2 to simplify, I mean, J1, J2, right? So, here you have 9, say d equal to 3, so you have 9 independent objects, right? So this rule tells me, I mean, this transformation rule tells me how these 9 guys will transform. Again, it will be some linear combination of those 9 guys, right? So I can write this whole thing as some big matrix, a huge matrix, right? A 9 by 9 matrix. No? You can do that. I mean, maybe I will write it down more explicitly later. Try to write it in this language. I will try to write it down that way. But for the moment, we just look at this here. Okay, so let's just fix on 2 for the moment 2. Then it's clear that the generalization is straightforward, right? From 2 to any, you can then keep increasing the number of indices. So if you understand for 2, second rank tensor, I think you understand everything, right? Okay, this is at the level of group. Okay, this I don't know if you have seen in the relativistic. You have done relativist, special relativity, right? So you have not done the second rank tensor, right? So you remember how the Lorentz group acted on this second rank tensor? It acts. I mean, each of the index will be transformed under the Lorentz group simultaneously, right? And the group, and the level of group. But now let's ask the question: what happens at the level of algebra, the Lie algebra, G? So that this just means that I'm taking the G to be 1 plus some small infinitesimal thing, right? And then just substitute that here and take the first order x, right? That's all what I was doing. So in this case, you see what you'll get, it will be a sum of terms. Huh? So for example, I can make this 1 plus x, I put 1 plus x here and 1 plus x here. So this will be the same as, so Rf of 1 plus x will be identity. Okay. Identity, whatever the d by d identity, right? I mean, this is all this is a d-dimensional representation. So d-dimensional identity, d by d identity plus r of x, right? This is already first order. This is again a d by d matrix. So similarly, I can do it there. Okay, but I want to pick from here only the first order. So this will become a sum of 2 terms. One where you have just the r of x acting on the first index, I1, J1. And the second guy, I take the identity, right? So it will be delta I2, J2. And the second term would be the other way. So delta I1, J1, R, X, I2, J2. I2, J2. This whole thing multiplying T, J1, J2. To the first order. We are only keeping the first order. Whenever we go to the Lie algebra, we keep the first order. Of course, the first term is identity itself. First term is just T, I1, I2, which means when you take the product, identity from here and identity from there. Okay. Plus one. But this is just the identity or action, right? The first order term is that. So this is what the Lie algebra does. The algebra is doing you look at the first order variation, right? First order variation is that. So you see, this is a sum of terms where each index is acted upon by Rx, and it's a sum of those terms. So you act on the first index, but do nothing on the second index. That is this term, right? This term is acting on the second index, but nothing on the first, identity on the first. That is this is just a consequence of the way the group acts and the way the Lie algebra acts. So Lie algebra always becomes additive because it's the first order. That's why it becomes additive. Okay. So now, what can we say about it? So just to continue on the questions you're asking. So let's just take a simple example. Let's suppose, to write 3 by 3, 3 times 3, 9 by 9 matrix will take a long time. So let me just take D equal to 2. Let me take D equal to 2. So each of this index, T, I1, I2, this index is going from I1, each of these indices is going from 1 to 2. So I'm taking D equal to 2, just so that we can write the matrix in a finite amount of time. So there are 4 components. So one way to arrange these components is the following. T, so keep the first guy fixed, say 1, and there I can have both. So think of this as a vector. Vector now, T1 is a vector with the index I2. Okay. So now because I fixed the first index, so only the other index is now moving, changing. Right? So this is like a vector. I don't know how to shall I put it. And then T2, a vector. Okay. So what it explicitly means is, now I can open this up also. So this is like T11, T12. This is a vector, it's a 2-column vector, right? Because I2 is going from 1, 2. So this is a 2-column vector and that's a 2-column. Maybe this is not a good notation. It's a 2-column vector. This is a 2-column vector. Okay. So first column vector, I just write explicitly now. And then I have a second column vector, again T21, T22. You can do that. Now let's take, in fact, since I'm doing D equal to 2, let's look at the SU2. SU2 is fundamental representation is 2, right? So suppose the group is SU2, or Lie algebra SU2. And I'm applying, say, sigma 3. Okay? I'm looking at where I take this X to be sigma 3. So how will I write there? So first of all, you see sigma 3 is acting on each of these index separately, right? We said there's one term where sigma 3 acts on the first index, and then there's another term where sigma 3 acts on the second index. So when it acts on the first index, what it is going to give me? It doesn't see the second index, right? Second index is identity. When the first term. So that will be simply given by identity here and a minus identity here. I write it as minus identity because this, remember, is a 2-column vector. So here, this is a 2 by 2. These are blocks. There's a 2 by 2 block here, and that's a 2 by 2 block. That's it. But then I have another term where it acts on the second index. But in second index, what's happening? It doesn't do anything on the first index. Meaning the way it acts on the first index here, the way it acts on the T1 column vector will be the same as the way it acts on the T2 column vector. Because On the first index is an identity, right? This term in the first index is identity, right? In the second index, I have a sigma 3. Okay? So this will be, again, in this block form, it will be sigma 3, 0, 0, sigma 3. No? Because, you see, when it acts on the second index, it is just rotating, I mean, it is acting on these two, this 1, 2 index. Huh? The SU2 will, Lie algebra will be just transforming the 1, 2 index, the second index. It doesn't do anything to the first index. So, and here again, it will not do anything to the first index, only the second index. But both of these guys will transform in the same way. Because the way it transforms is insensitive to the value of the first index. It doesn't care about the value of the first index. Right? That's why these both are sigma 3. No? Here, the second term. Whereas first term is this. The first term doesn't care about the second index. So it will act as a whole on this vector, this column vector. Right? So it will be, so 1, it will act as 1 here and minus 1 here, because that's the way, that's a sigma 3 action on this 1 and 2 index. No? Okay. So this is, so actually if you just rewrite that whole thing, I mean explicitly as a 4 by 4 matrix, you see this is, so this will be 2. Okay, let's make it, instead of sigma 3, let's call it H. Let's apply R of H, huh? Where H is sigma 3 by 2. That is just to get rid of this factor of 2. I mean, no, it's not important, but okay. So it will become 2, 1 half, 1 half here. 1 half, 1 half, and add it up. So you get here 1, here. Remember this identity is what? If I put right in gory detail, it is 1, 1, 0, 0. And here it is minus 1, minus 1, 0, 0, right? And then just add that up. Sigma 3, here is 1, minus 1, 0, 0. And here is 1, minus 1, 0, 0. And then just add that up, you see 1, 0, 0, minus 1. Diagonal matrix. So because we said that there are 2 times 2, altogether 4 components of the T. So this is giving you a 4-dimensional representation of SU2, right? So it will be 4 by 4 matrix, and this is the way sigma 3 acts. Huh? Same way we can construct sigma 1 and sigma 2. Let's just do that just to get some experience. So now suppose I want to construct to see how sigma 1 by 2 acts. So R sigma 1 by 2 in this on this tensors. So again, let's look at this here. First, I look at the T1, T2, right? So this is each of them is a 2-column vector. So this is a 2-column vector, and I'm writing it as a block. So when I write it as a block, how is it going to act? It's going to act as sigma. So sigma y. So this is going to just transform these guys. So it's going to be identity and identity, right? 1 half. Because what sigma 1 will do, it will exchange 1 with 2 and 2 with 1. It's acting on the first index, remember. Right? This doesn't care about the second index. So on the second index, it will be always identity, proportional to identity. It only cares about the first index, and that's the way it does. So here is an identity matrix here. The 2 by 2 identity matrix. That's the first term, the analog of that. So where it acted on the first index. Then the second term would be, so the second term would be, so now I look at again T1, 1, so I open it up, T1, 2, this is the first one, and then the second one was T2, 1, T2, 2. So the second guy, this term is acting only at the second index. It doesn't care about the value of the first index. No? Totally irrelevant. So that it is just going to exchange these 2 and these 2 in the same way. It doesn't care about how the first index, so it will be the same way. So that will give me simply sigma 1, so half sigma 1. So half is sigma 1, this will be now 0, 1, 1, 0. And then in this block form, here it is 0, 0, and here it is 0, 1, 1, 0. The second term will be always block diagonal because it doesn't touch the first index. The second one doesn't touch the first index, right? So these blocks were differing only in the value of the first index. So since the first index is not changing, that will be always block diagonal, the second guy. So now you can add that up, and so yeah, I mean this is all 0, 0. Here it is 1, 1, 1, 0, 0, and 1, 0, 0, 1. So if you just add that up, it will be some 4 by 4 matrix. And the same thing you can do for sigma 2. Right? But I hope you see, of course this process, I mean if you want to do it for a large value of D, and not just second rank tensor, but say 10th rank tensor, you will probably fill up the whole book, whole notebook, you know, trying to. So it's not very efficient. But this is just to give an idea what are we meaning by this. I mean, so this is some 4-dimensional representation in this example. Okay. But this is not reducible. This is not irreducible. This is not irreducible. Okay. We'll see that now. Why it's not. So let's just yeah. But before that? Is there any question here? I mean, in physics, many times you have this situation. You have some, let's say, as I mentioned, we have a composite particles. Say, imagine there's some one particle decays into 2 particles, right? And so, since these are conserved quantities, these guys are, I mean, they're symmetries, right? So this, all these things that we're talking about, they're conserved objects, right? So if I started with a spin J, SU2, whatever comes out, okay, one of them will be spin J1, other will be spin J2, but in such a way that the combination must be must be the original J. So many times you want to ask the question, how is it possible? I mean, maybe sometimes it's not even possible. It may not be that all the possible J1 and J2 can come out. No? For example, let's say if I take I mean, one spin half, okay, spin half particle. Now from there, and it decays into 2 particles. Let's say these 2 particles, it cannot be that both are spin half, no, because spin half is plus spin half times spin half gives you either spin 1 or spin 0, right? It's never spin half. Okay. So that's why, I mean, it is sometimes it's quite important to, for physics, from the physics point of view, it's very important to decompose these things in terms of irreducible representations. We'll see first of all, we'll establish first of all that these tensors are not irreducible. Okay. And then the next question arises, okay, can we reduce into irreducible representations? Hmm? Okay. I mean, yeah. So, what is the definition of reducible representation? It means there is some invariant subspace, right? A proper invariant subspace. That is what. So now so what I want to go through is to show that this has proper invariant subspaces. Okay. So let's do the following. So I have, let's say, just take the rank 2. So you have I, J, two guys, 2 indices. Let's start with the two of them. There is generalization of that for arbitrary. But 2 of them. And let's take the symmetric combinations. So I will denote Tij. When I put a bracket like that, I mean symmetrized. This is usual notation that in physics literature that people use. This kind of notation means I have symmetrized. So what it means explicitly is simply is half Tij plus Tji. Okay. So this is actually, I mean, this is clearly symmetric. When you exchange I and J, you don't get, it's the same thing. Or you use the symbol square bracket ij, and this indicates antisymmetric. So this is a notation, just to simplify the life. So now what we want to show is that each of these spaces is invariant under the symmetry group. So therefore, that shows that it's a reducible representation, if you can show that. So let's see how it will transform. So let's look at the Tij first, how the Tij transforms. So Tij will transform as G Ik Tkj. Now I'm going to use, I don't want to keep writing the R there. When I write xik, okay, when I write x, I mean the representation. Because otherwise it takes too long a time to write.
You're already in fundamental representation. So
Yeah,
that means,
true.
Rx is already x.
Yeah, correct. Well, okay, I mean, yeah, true. Because we are dealing with the matrix groups, right? The groups themselves are defined in terms of matrices. But if you define group abstractly, then okay. Well, yeah, so let's just say with the abuse of notation, I just use the same symbol, otherwise it takes too much time. So then plus x jk t I k, right? That's what it's saying. The first it acts on the first index, doesn't do anything to the second index. Second index was j here, right? And it transformed like x I k, okay? And then the second guy is where nothing happens to the first index, and the second index is transformed like that. This is how we define the way the Lie algebra acts on the tensor product. I mean the tensors. Okay, so and then similarly, what will happen to Tji? So we have these two terms, right? Tji. Well, again the same rule. X jk tki plus x ik tji jk. Okay. Now let's look at this. Take the sum of them or the difference of them to get these two expressions, right? So if you take the sum, so if you just add that up, so Tij, I mean, sorry, what is this notation? I mean, this goes to, right? This transforms to.
Isn't there also plus self term?
Plus what?
Plus one term.
Plus one. No, that is the. This is the infinitesimal change. This is the infinitesimal change. Yeah.
Difference between the old and
Yeah. Correct. This is the infinitesimal change. Yeah. So maybe if you want to put delta here, change. No? But okay. Okay. So now let's take the sum and the differences. Here now, what will I? And let's collect the terms which have the same xik. So we have, if I collect, so let's look at the Tij, and in fact let me do both at the same time. Plus minus Tji. Right? How it will transform. So this will transform to this plus minus that. Right? And then in that thing, let's collect the xik term and xjk term separately. So this will be, if I take xik term, this goes to tkj plus tjk. I mean this term plus or minus. So xik is here, xik is here, right? So I take, so this is tkj plus or minus tjk, right? Depending on the sign here. And then I have similarly xjk, this term, there are this term and this term. So I will get here tik plus or minus tki. Okay. So you see that this is, so the way it's happening, if I had taken the plus sign, it is only going to mix with the plus signs, right? So if I had taken the plus signs, it will be invariant. That space will be invariant under this transformation. And similarly, if I had taken the minus sign, again that will be invariant. So that proves that this space is not irreducible. It's a reducible representation. No, so just look at this. I mean, so if I take this object Tij, right? This is by definition. That is just this with a plus sign, right? Half. Okay, forget the half. Half is not important. The half will be both sides. It's not important. Right? So if I take the plus sign, if I take the t, so let's just write down. So from there, I conclude that Tij symmetrized, this object, will transform like xki kj symmetrized plus xjk tik symmetrized. You see from that experiment. So in other words, this doesn't mix. I mean, after all, any second rank tensor I can split into symmetric and antisymmetric parts, right? But what this is saying is that a symmetric part will never, when you do the transformation, it will never includes anything from the antisymmetric. Symmetric matrices will only go to the symmetric matrices, and antisymmetric will go only to the antisymmetric matrices. Okay? So that's what one is saying, right? Is it clear? So I mean the full space. Let's take the example of d equal to 2 and second rank tensor. So we already saw it's a 2 times 2, 4 components are there, right? If you take the symmetric one, it will have 3 components, and the antisymmetric one will have just 1 component, right? So what we are saying is that if I started with this symmetric one, one of these 3, and I do the transformation, I'm never going to end up with the antisymmetric one, and vice versa. You see, so I can split. So in the previous example, I can split that what we were writing, this T11, T12. I can rewrite this in a slightly different combination. I can take it to be T11, then the combination T12 plus T21 divided by 2. This is not important. Then you have T22, and finally a combination half T12 minus T21. And what I'm saying is that the matrices that you will get by if I change the basis, we wrote this matrices in this basis, right? But now rewrite that matrices in this basis now. Okay. Then you will find these matrices become block diagonal. You know, so in this basis, all of these matrices, maybe you can try to do this. Since if you have already the sigma 1, sigma 2, sigma 3 in this basis, right? Now just change the basis into this combination. And you will find that in this basis, all of these matrices will be block diagonal. So you have this is a 1 and 3, right? This is a 1 by 1. I mean, there's 1 and sorry, this is 3. This is 3 and 1. So this is a 3 by 3 matrix. This is a 1 by 1 matrix. This is a 3 rows and 1 column, and that is 1 row and 3 column. Then you will see that this part is all 0, and here it is something. Here something non-zero. Okay, and here it is 0. Okay. I mean, here it is 0 just because it's a very special case, because we are looking at it's a one-dimensional representation, right? Because for d equal to 2, the antisymmetric thing is only one-dimensional. Okay. D equal to 2 because it's a half d minus 1. If d equal to 2, then this is 1. It's one-dimensional. And when it's one-dimensional, that means it's invariant. A one-dimensional representation is a trivial representation, okay, where the group simply doesn't do anything. It just gives you back the same vector. Okay. And in particular, the Lie algebra will annihilate it. So that's why it is 0. That's just because d equal to 2. In general, it will not be. So if I take d equal to 3, then I will split 3 times 3 by 3 times 4 by 2, so 6 and 3, right? So let's take, maybe because this is a bit misleading. If you take, let's say, 3 by 3, I mean, d equal to 3, so you take ij, where I and j go from 1 up to 3, 1, 2, and 3, right? Then this dimensionality, the total number of components is 3 square, which is 9. So total is 9, total, which is 3 square. But if you look at the symmetric guys, the ones which are the Tij component, that will have how many? It's just 1/2 times 3 plus 1, right? which is 6. Whereas if you take the antisymmetric one, ij, this will be half 3, 3 minus 1, which is 3. So in that case, you started with this in this way of defining. Okay, you have to do a bit more work, but it will be 9 by 9 matrix. All the generators will be 9 by 9 matrices. Of course, now we are not talking about SU2, right? Okay, if you insist on fundamental representation, it's not SU2, but you don't have to. You can take the spin 1 representations for SU2. No? That's also possible. But anyway, so then you can go back and show that if you go to this basis where you take the symmetric part, this is 6 components. So write the column vector like the 6 and 3, where these are all symmetric ones and these are antisymmetric ones. Okay? So this is a changing the basis from there to symmetric guys and antisymmetric guys. And then in this basis, you will see that all the generators will split into a block where these parts are 0. And here is something, here is something. These are non-zero, but that is the meaning of reducible representation, right? So therefore this space is invariant, meaning if I started with a vector here and do the transformation, I will never end up there, and vice versa. Okay? So this is reducible. Yeah.
So this claim is always valid for any tensor representation, because you can always decompose any tensor. You can specify any. But we just listed all the entries from the tensor like a vector and looked at the possible matrix forms that are transforming the tensors, and we block diagonalized that created matrix.
Yeah.
But it is not. You cannot see it from the transforming tensor.
Well, I mean, we obtained this form, all this 4x4 matrices I wrote was from that original definition of the transformation on the tensor, right?
But the transformation itself was also not a matrix in the beginning. As we transformed the tensor into a vector, the transformation for the tensor become a matrix, and there you look for reducibility.
Yeah.
And if you reduce it there, it means that the tensor transformation in a higher rank is also reducible.
Yeah.
So we can make this
Sure.
yeah.
But if the D is very large, it's not very economical to write down these huge matrices. No? In that case, you just work with this kind of thing, symmetry properties. So basically, what you do is you take the tensor and look at this was an easy thing. This was only rank 2. Rank 2, the only thing is the permutation group. But basically, symmetry group means symmetry. I don't mean I should make it clear. There are two symmetries here. One is the symmetry that we're talking about, SU2, SU1, etc. Yeah? Okay? But here, now I have the two indices here, right? So there is a discrete symmetry, which is the permutation symmetry. It's nothing to do with the original group. Yeah? This is a permutation symmetry of the indices. This is a discrete group. It's not a continuous group. And what we did when we decomposed in terms of symmetric and antisymmetric part, it is just under the action of this permutation. One of them gives you a plus sign, other gives you a minus sign permutation. No? So it's basically looking at the permutation group. But for the two indices, it's very simple. Permutation group is simply Z2. No? But you already saw when I think we studied the example of the 3-index permutation group. But permutation, if there are n indices, permutation group Sn, we call it Sn, it has factorial n elements. So it's a very huge group. So for example, for 3, n equal to 3, if there are 3 indices, factorial 3 is 6, right? So there will be 6 elements. Those are discrete group elements. This is exchanging of the indices, no? Various possible, or cyclic rotations and so on and so forth. No? So it is just basically decomposing these indices in representations of the permutation group. That's what we did here now for the 2-index. And you have to do the same thing for 3-index and so on and so forth. And that is the way you get irreducible representations. It starts becoming difficult for if you say rank 3. because then we have a permutation group of 3 elements, which is a bit of a mess. But before going to that, let me just, so this particular SU2 case, in say SU2 we already know the representations. Now, what are we doing here? Let's see. So to try to convince you that indeed this is what you should have expected. That, so in the SU2 case, this was 4, altogether was 4-dimensional. The symmetric part was 3, antisymmetric part was 1, right? 1-dimensional and 2-dimensional. But the dimension is 3, that is spin 1, right? In our language, 2j plus 1. So 2j plus 1 is a dimension of the irreducible representations, right? And for the spin j representation, whose dimensionality was 2j plus 1, right? And that was irreducible. Now this 3 corresponds to j equal to 1. And 1 corresponds to j equal to 0. So on the other hand, if you look at each of these index, this was like fundamental representation. So spin half. Fundamental representation, spin half. So what we have done is we have taken the tensor product of 2 spin halves, okay, and then decompose it into irreducible representations. The product of 2 spin halves will exactly give you spin 1 and spin 0, right? Okay. Now maybe the rest of that you have seen it, I think, before. Probably you have seen it in the quantum mechanics course, you know. But just from this point of view, we can try to work out, try to, in the language that we were using yesterday or day before yesterday, to get all the representations of SU2, where what we did, we looked at the kappa, which is sigma 3 or h, little h, and then take the highest weight and then construct all the representations, right? So now let's look at this case. So what we have, so I'm going to write now this different components of tensor in terms of the eigenvalues of h being the kappa. Okay? Remember, the way it acts, so in a tensor Tij, so we had, it acts as two terms, right? So the way it acts is one is a Rx acts on the k plus T plus R j k T I k, right? So individually it acts on the first index, then it acts on the second index. It's a sum of 2 terms, right? So instead of using this basis, since I have I is equal to 1 and 2, I and j are 1 and 2, right? Instead of that, let's use the basis where I have already diagonalized the h, right? And I will label the I and j by the eigenvalues. So I will have 4 components. I will have component, say, plus, or t plus minus, t minus plus, and t minus minus. So what I mean by that, this corresponds to plus half, because j is half. I don't want to write a half, otherwise it becomes very messy. No? Plus half, plus half. By this plus, I mean it is h quantum number is plus half. And when I write minus, I mean minus half. So this means both the indices correspond to plus half, plus half. This one corresponds to plus half, minus half, plus half, and minus half, minus half. Okay. So now when I apply h on this, I mean in this big representation, what am I going to get? As we said, in the big representation, h will act on this index plus another term where h acts on that index. This additive, right? When h acts on this index, it will just give you the eigenvalue of that, which is plus half, right? When it acts on this index, again it will give you plus half. And it's additive, so plus half plus half is 1. Okay? So h acting on this guy will give me 1. And these are all eigenstates, by the way. Right? I mean, each of these indices is eigenstate of h. So it's not going to mix anything. So this will be a diagonal matrix. Okay? Here is 1. And here, this will be plus half and minus half. So it will be 0. So this is a diagonal matrix. Sorry. Difficult to write. So everything is 0 here. 0, 0, 0. And here again 0, 0, 0, 0. And here you'll get 0, 0, 0, minus 1, because it will be minus half, minus half. Okay? So that's the reason. So by now looking at this, so what is the high, I mean in this representation, what is the highest value of of h? It is plus 1. Okay? Nothing beyond it. That means this must be highest weight state. Okay? J plus must, sigma plus must annihilate it. Okay? If it does not, then, I mean, we know for sure this is a representation. It may not be irreducible, but it is a representation. So, on the other hand, we also know that sigma plus will always raise the eigenvalue. But the maximum eigenvalue is 1. So, it must annihilate this state. Okay? Sigma plus should annihilate this. And similarly, this will be the lowest weight. Sigma minus should annihilate it. So, given the fact that I have a highest weight state with the spin, which is annihilated by sigma plus, and whose quantum number, h quantum number is 1. So I know there must be one irreducible representation, because we have a complete classification of all irreducible representations, right? So, which are characterized by simply the highest weight, right? So given this fact of highest weight, I must have a spin 1 representation. Okay. So what are the spin 1 representations? Spin 1 representation, spin 1 representation will have 3 states. It's a dimension 3, 2j plus 1 in dimension 3, and its eigenvalues of the h, eigenvalues will be plus 1, 0, and minus 1. Okay. So this state, and a particular combination of these two states will provide you these 3 states. But then what is left over is the other combination, right? But other combination is spin. So let's say some combination, t plus minus plus something, I don't know, plus some coefficient, I don't know. You know what I mean, some coefficient, x, t minus plus. Let's suppose this is in this is what that state is, right? But then what about the other state, the remaining state? That the remaining combination actually turns out that this is just a symmetric one. One can check it. One can check it. Okay. Because you see, I mean, whatever the state here is, right? This, when I apply sigma plus on this, I mean, this is the state here, right? I'm talking about this state. When I apply sigma plus on this, it should go there, right? Or when I apply sigma minus on this state, it should go there. Now, if you apply sigma plus on this state, sigma plus will not act on that, because this already, I mean, it's additive again. Remember, each of this index sigma plus will act independently, and then you add the result, right? When sigma plus acts here, it doesn't do anything, because it's already the highest weight of the spin half, right? But when it acts here, this minus will become plus. So it will indeed go to t plus plus. But the same thing will happen with this. This will also go to plus plus. Okay? Because the first time, the first action, the first index was annihilated, but second index took, I mean, the sigma plus took minus to plus. Here, the second index is annihilated, but the first index from minus will go to plus. So both of them give t plus plus. Okay? So if I had chosen a minus sign, it will give you 0, because it cancels. So a minus sign will not, this will not be the minus sign, it will be the plus sign. Okay? So you basically decompose this combination into a symmetric combination and antisymmetric combination. Symmetric combination is what will appear in this representation. Okay? And then there's one more state which is remained by just looking at the counting. How many states are there with the J3 quantum, H quantum number 0? There are 2. Here I've taken care of 1. So one more is left over. But this has nowhere to go. There's no sigma plus sigma minus, just that. So it must be spin 0 representation. Okay? So this is a way to think about that. Huh? So antisymmetric guy will be the spin 0 representation. I mean, this procedure, okay, we did the tensor. Since I have just a few more minutes, let me just do this. I mean, in general, you see, if I have not the tensor, but I just take the tensor, product of 2 representations. Okay. one particle transforming in a spin j representation, another particle in some spin j prime representation. Okay? Then you can ask the question, what will be the, when I decompose it in terms of, this product will not be an irreducible representation. Then the question is, if you reduce it into irreducible representations, which spins will appear? No? That's a natural question. So what appears is, so let's take, so let's say spin j1 and spin j2, two representations. I take the tensor product of that, meaning like one object transforms like that, another object transforms like that, and I look at the composite, the combined. So, so this, now again, let's write down the quantum numbers of H. Right? So here it will start with a plus J1, so yeah, J1 minus 1, etc., minus J1. Okay? Here I will start with J2 minus 1, and so on, minus J2. Okay? These are the H quantum numbers. So when I take the combined, the tensor product, it will just be additive. Just add, right? Because this guy is going to act on this index, I mean this thing, and nothing on that, plus another, plus identity here and H, the tensor product representation. That's what. So then the combined H eigenvalues will be, you just add them. So it just it will go from J1 plus J2. It will be J1 plus J2 minus 1, and so on. Let me just write down one more, J1 plus J2 minus 2, and all the way up to minus J1 minus J2. Okay? That's the way it will be, right? Now let's count how many states for each eigenvalues are there. Here clearly the multiplicity is only 1. So now I'm writing down the multiplicities. Here there is only one state, because the only way I can get J1 plus J2 is if I just take this and that, nothing else, right? But here, in order to get that, I can take this one and that one, or this one and that one. So I have multiplicity 2, right? So there are two states here in this tensor product. There are two states which have the same eigenvalue, H eigenvalue. Now let's look at this guy. Now I have even more possibilities. So let me write down, so J1 minus 2, J2 minus 2. I can take this guy with that. Sorry, I can take this guy with that, but I can also take this with that. So there are three states. And okay, you can keep going. I think, yeah. Again, the minus J1 minus J2, there's only one state, one possibility. Because this is the lowest value, this is the lowest value. Okay? So here is again 1. Now looking at this table, already you can see what is happening. So clearly highest weight of this representation is that, J1 plus J2. That's the highest possible. So I know there is a spin J1 plus J2 representation, right? So there is a spin J1 plus J2, so there exists for sure a spin J1 plus J2 representation. And what's the dimensionality of that? It is 2 times J1 plus J2 minus 1. Right? Remember the total number of states here. This has 2J1 plus 1. That has 2J2 plus 1. And tensor product is a product. Dimension is a product. So the dimension of this representation is 2J1 plus 1 times 2J2 plus 1. So it's a huge number. For large J1 and J2 is a huge number. It's quadratic, you see. Right? Whereas here it's all linear. Plus 1, sorry. Right, plus 1. So that's 1. Okay, but you also know that in SU2 we have already gone through that at each H quantum number, in a given irreducible representation, at each H quantum number, there's only one state, there's no multiplicity. Multiplicity is always 1, right? So this representation will have H quantum numbers, J1 plus J2, J1 plus J2 minus 1, and so on, all the way up to minus J1 minus J2. Okay? Okay, so I remove that. Now I look back at what is remaining. So this I know is this one irreducible representation. What is remaining here is this state has been taken care of. These two states have gone into that representation. But here there are two states of which one combination goes into that. Okay? But the remaining combination is left over. There's one combination left over. And that combination will be a highest weight now. Because it cannot go to J1 plus J2. It should be annihilated by sigma plus. Because this guy, in this representation, when I apply sigma plus on that, this will be mapped to that. Right? But then there is a kind of an orthogonal, let's say quote unquote orthogonal combination, a linearly independent combination, which is left over, which is annihilated by sigma plus. So that's going to be a, because I mean it's clear, right? I mean you have two states, and sigma plus is mapping to one state. There are two states with the J1 plus. Two states are mapped to one state, right? So you can always choose some combination such that that combination is mapped to that one state, and other combination is mapped to 0. No? That's so there will be one combination which is annihilated by sigma plus at this level. At the right? So that is going to give me another irreducible representation. Okay? But how many such? There's just one, because one of them has gone. One of them has gone here. So there's only one. So then we see that there is also, not only that, there is also a spin J1 plus J2 minus 1 representation. Okay. Now let's go to the next level. So at this level, there are three states. One state has gone into this representation, and another state has gone into that representation, but we are left with one more. Okay. So that is going to be now, there's going to be one more highest weight state, right? So this process keeps going. Okay. At some point, it depends on the value of J, which one is bigger, J2 or J1 is bigger, At some point what will happen is that this multiplicity will reach a maximum, and then it will stay the same. You can I mean, just try to, for example, let's say, I don't know, let's take, I don't know, J1 equal to 2 and J2 equal to 1. That is already 15 stages, a lot. Okay, but 15 stages. So let's take J1 equal to 2 and J2 equal to 1. Okay, so the highest is 3. So then we have to, it's a bit of a mess. I don't know whether this phenomenon you will see. 2 minus 1, 2 minus 1, so 2, 3, 4. Yeah, I think you'll see this phenomenon here already. Of a kind of a saturation. That as you see, this keeps increasing, right? But it cannot go on indefinitely, because here it keeps decreasing, the negative side. Because negative side finally you should end up with 1. Right? So, but sometimes depending on the relative values of J1 and J2, so if I take J1 equal to 2 and J2 equal to 1, so what are the possibilities here? 2 plus 1, H quantum numbers. So this is right nearby, J2 equal to 1. So you have a 3, 2, 1, 0, minus 1, minus 2, minus 3, right? Multiplicities, one state here, 2 states here. Maybe I should better write. To get the multiplicity, let's better write like first do it in 2 steps. So this is plus 2, 1, 0, minus 1, minus 2. This one is 1, 0, minus 1, right? And now I add them up to get the, so when you add it up, so J1 plus this H1 plus H2, the eigenvalues of the H2 will be 2. There's only 1 2 here. No, sorry. 3. Huh? 3. 2 plus 1. Sorry, 2 plus 1, 3. That's the highest. Okay. 2 plus 1. Then let's look at the 2. How many are there? 2 with 0 or 1 with 1. Right. So 2 states. So this is 1 state. Here is the 2 states. Now look at the 1. How many ways I can get 1? 2 minus 1. Or 1, 0, or 0, 1, right? So 3 states. Now look at 0. Now you see 0 again is 3 states, right? Because this 2 cannot pair with anything to give you 0. Right? So this with that, and that with that. So again 3. And then the negative side it will be as a repetition of this. Okay, so minus 1 will be 2, minus 1 will be 3, minus 2 will be 2, and minus 3 will be 1. Okay. And now you can immediately see, just from looking at these numbers, what representations will appear. Okay. One, there will be spin 3 representation. So once I have taken the spin 3, I remove 1 from here, I remove 1 from there, to still left over 1. I remove 1 from here, so 2 is left over. 1 from here, 2 is left over. 1, 2 left over. 1, and this is gone, right? So this was spin 3. Now what I see, there's a highest weight for which is spin 2, right? So then I'll have a plus spin 2 representation. So spin 2 representation will take care of that. One of these, but 1 is still left over. One of these will be still left over 1, and this goes out. And now what is left over? This is the highest weight here. So you get here spin 1. And that's it. Spin 1 takes care of everything, nothing left over. So that's the total, that's how it splits. And you can count the number of states. This is spin 3 is what? 3 times 2, 6 plus 1. So there are 7 states here, there are 5 states here, and there are 3 states here, right? Which is 15 states. And here you have 5 times 3, 15.
Yeah. Is it always like some of different spin J representations, or can it be like 2 different spin 2 representations too?
Do you repeat that again?
We just saw that 3, 2, 1 are all different spin representations, spin 3, spin 2, and spin 1.
Yeah.
Can it be like spin 3 and 2 spin 2s and 1 spin 1 or something like that? Is the pattern always like
in this case, I mean, at least for SU2, it always comes with in this structure, because you can see that from at least if I take the only 2 products, I mean, you can have 3 representation of 3 products of 3 representations, then it's different. But if I just say spin J1 times spin J2, then it always appears once only. Because the structure is always like that. Multiplicity increases by 1 unit, not by 2 units. No? Because the combinatorics, various combinatorics is such that highest one, 2 plus 1 comes with 1. But then you go to the next one, you just reduce these guys by 1. So there are only 2 ways of getting it. No? 1 less, you go only maximum 3 values, of 3 ways of getting it. So it's always 1. But of course, if you can take triple product, then you can start getting repetitions of various same things. Yeah, so this is the basic way of understanding how it works. I mean, how the... Of course, it's, I mean, in practice, if it's a very high dimensional representation, SU2 is still easy. I mean, the rule you already know. I think from the undergraduate, you already know that if I take J1 and J2, I take the tensor product of this representation, then you decompose into irreducible, which is J1 plus J2, the highest, plus J1 plus J2 minus 1, all the way up to J1 minus J2, whichever the absolute value, J1 minus J2. Right? That's indeed exactly what we found here. You have a spin 2 and spin 1. So you have a 2 plus 1, 3, 2 plus 1 minus 1, 2. And then the 2 minus 1, absolute value is 1, right? So it stops there. You don't get a 0 further lower than that. And the reason why, because this number was the same, 3. And this didn't increase. Okay. If it had increased to 4, these are multiplicities. If this had increased to 4, then you would also get a spin 0. But that is not happening. This is the reason why you had this, this structure. That is straightforward. Okay. So I will then continue. I think I will at least maybe take another half of the Monday's lecture on I mean the tensors, Tij, and go to the third rank tensor. Just describe the third rank tensor, what happens with third rank tensor. To give you, I mean, to kind of convince you that it is, okay, it becomes more complicated. And the way then to classify these representations is something called Young tableau. Okay. The Young tableau is closely related to as you can see from this discussion, that this whole problem is closely related to the SN, the permutation group. No? What kinds of possible representations are there in the permutation group? And so the Young tableau is precisely the right language to talk about the representation of permutation groups. That's why Young tableau plays an important role. I won't be spending too much time on the Young tableau because otherwise I will not be able to go into the SU3 and so on. So I will just briefly mention to you Young tableau and some rules on how to use this. Because to go into the permutation group, representation of the permutation group will take a long time. Discrete group, but it's a rather complicated group. Permutation groups. Okay. So yeah, we'll stop here. Any questions? Any questions? Okay, think over it, and tomorrow you have the tutorial, right? So please ask a lot of questions, both to, the tutorial as well as here in the class. You should ask as many questions as you can.